Hi, this is Nasnianevsky. This class is analysis of algorithms. We're doing Corman, Lyson, Revest, and Stein's, the third edition. Homework, chapter 7. These are the problems we're going to be doing. And we start with section 7.1-1. Again, as always with all homework, you should first be doing it and then check your answers here, but we're doing it. Okay, I thought this was also a good time to review this partition algorithm because it's a little bit what's the word? A little bit complicated. Okay, it's on page 171. Okay, and but I rewrote it here. And basically, what it does is it splits up the array into 4 parts. And again, we did this in class, but it splits up the array into 4 parts. Okay, and this part is everything less than x, where x is here, the pivot. That's the pivot. Now the pivot is in position R. Okay, and this part is everything greater than x, and this part is unseen. Okay, but we have to be a little bit careful about the indices. This is P is right over there, I is right over here, and J is right over here after that boundary. Okay, okay, and basically what we're going to do is we're going to go through all the cards, all the elements, and anything that's less than x goes there, anything that's more than x goes here, and we slowly go through them and swap them when we need to, and we're going to finish this off, and at the end you're going to have like this. Okay, there's not going to be anything unseen. You're going to go through everything. Everything is going to be less than x here. Okay, more than x here. I think I goes here, and this is I plus 1. Okay, and this is more than x, and what you're going to have is x is over here. So that's where you're going to partition the elements. Okay, so the homework problem for section 7.1, number 1, is take this and do it exactly like the book does. The book does it on page 172. They have their example, and we're going to go through our example. Okay, so it goes as follows. Let's go through it. This is going to be, I is going to be here. I'm not going to do it with different colors because it's just going to take more time. So this is x is equal to I of r, so we're going to pivot around 11. We're going to pivot around 11. Okay, again, everything less than 11 is going to go here, everything more than 11 is going to go here. So A is the array, P is your starting place, R is your ending place. Okay, x is equal to PR, that's what you're doing. I is equal to P minus 1, go backwards a little bit, so over there. And for J is equal to P, that's from here till R minus 1, until you get to the pivot. You don't touch the pivot, and here's the main line. If A of J is less than x, let's go through what that means. If A of J, the thing that you're looking at, is less than x, that means it has to go on this side, and here's what you do. You move this to I plus 1. You move it further, okay, and then you exchange. So let's do it. So, let's do it. 13, is 13 less than x? No, 13 is more than x, so we're going to leave that alone. 13 is more than x, so we're going to leave that alone. I is equal to I plus 1, so we're going to move this. Now I is here, okay, and you'll see, explain it in a second. Oh, I'm sorry, we're not doing that. Okay, so we keep on going. So A of J is less than x. We want to know where's the first time that something belongs there. So 13 goes there, 19 goes there, 9 goes there. And so what we're going to do is here. We're going to get to 9, okay? J is here. Okay, and let's do it. A of J is less than 11. Yes, it is. It's less than a pivot. It has to go there. So then I is equal to I plus 1. So I goes here. I was over here. I goes there. And exchange A of I and AJ. So now what we do is 9 goes here. 19 is here. 13 is here, 5, 12, 8, 7, 4, 21, 2, 6, and 11. Okay? Okay, now we go further. Okay, we go further. 5. Okay, we're here. 5. 5 has to go there because it's less than 11. That's our pivot. So 5 has to go there. Okay, so what do? I is equal to I plus 1, so here's I. We increment I, and now we're going to exchange A of I and A of j. So here's j, and we're going to do it. You ready? So it's 9, 5, 13, 19, 12, 8, 7, 4, 21, 26, 11. Okay, great. Now we do j. Here's I. Okay. Notice these guys are less than 11. These guys are more than 11. These guys we didn't see. So I can even draw it in the way the book does it. A thick line here, a thick line here. So less than x, more than x, unseen, pivot. Okay, let's go further. 8. So now j is here, so now j is here. Okay, okay. 8 goes here, has to go this side, so what are we going to do? We're going to swap it. We're going to increment I to here. Increment I. 8 has to go on this side, and so we do it. We're going to swap 8, so we get 9, 5, 8, thick line, 19, 12, 13, thick line, 7, 4, 21, 2, 6, and 11. Okay? Okay, let's keep on doing it. Let's do it a little bit quicker. Okay, so we're now going to swap. We're getting to 7. We're going to swap 7 and 19. Okay, so it's going to be 9, 5, 8, 7, thick line, 12, 13, 19, thick line, 4, 21, 2, 6, and 11. Okay, all less than 11, all more than 11, all unseen. Okay, let's go further. We're going to swap this and this. Okay, because 4 has to go with that side. So it's going to be 9, 5, 8, 7, 4, 13, 19, 12, 21, 2, 6, and 11. Just check my notes. 1, 5, oops. 9, 5, 8, 7, 8, 7, 4. Okay, looks like we're doing it right. Okay, good. Now, next, 21. 21 stays here. Well, let's put in our thick lines. 4 is our thick line. Okay, we have 12. 21 stays on this side, so leave that alone. Okay, 2 has to swap, so we're going to swap. 13 and 2 is going to swap. So 9, 5, 8, 7, 4, 2. 19, 12, 21. This is 13. Okay, 6 and 11. Okay, let's go further. 6 goes this side, so 6 is going to swap with 19, so we get 9, 5, 8, 7, 4, 2, 6, 12, 21, 13, and 19. Okay. This is position number I. Here's a thick line separating it. This is position, oh, I forgot to write the 11. This is position there. Okay, and now what do we do? We exchange the I plus, so we finished. We went through everything till the pivot. We exchange I plus 1 and R. So let's exchange this and I plus 1 and this. Okay. Okay, so now we have 9, 5, 8, 7, 4, 2, 6, 11. That's your pivot. 11, that's your pivot. 21, 13, 19, and 12. Okay, some people, I think I got it right. Okay, so that's a nice final answer. Okay, and it returns, return, position I plus 1, that's exactly here. Return where the pivot is. Okay, that takes care of that. It's nice. You have to do it once in your lifetime very carefully and you'll get it working. Okay, okay, good. Next, problem number 4. How would you modify quicksort to sort into non-increasing order? Okay, so this is doing increasing. The things less than the pivot are here, the things more than the pivot are here, and you put the pivot in the middle. How would you do it the other ways? In other words, this is for problem number 4, how would you get it that everything greater than or x or greater than or equal to x would be here, and everything less than x would be here? And the answer is the simplest possible answer in the world. When do you swap? When should you swap? So here we swapped only when there's a guy, we swap when a guy belongs here. So when should a guy belongs here? Anyways, not when it's less than the pivot. Let's erase this because this is going to be confusing. Not when it's less than the pivot, but when it's more than the pivot, we want to swap it. So all we have to do is change this to greater than sign. That's it. And that will make you swap always when this is greater than, and otherwise it's just going to have less than. So that's a very nice switch. Okay, let's go to problem 7.2, number 3. Section 7.2. Show that the running time of quicksort is n squared when the array A contains distinct element and is sorted in descending order. So let me just explain to you why that's true. Okay, so let's take, this is section 7.2, number 3, show that the running time of quicksort is n squared when the array A contains distinct element and is sorted in decreasing order. Decreasing order. So let's pick a decreasing order. 23, 21, 18, 15, 12. These are separate, different elements. 9, 8, 5. Stop. Okay. So here's typical elements. Okay, now what happens when we do quicksort? Well, first we're going to have to partition. We're going to partition around 5. Okay, what's going to happen when you partition around 5? Well, all these elements are greater than 5. Okay, and so what you're going to have at the end is 5. And the way the partition works is it's just going to be like this: 21, 18, 15, 12, 9. 8, 21. Okay, good. Now, there's not going to be a left side, it's only going to be a right side. Whoops, sorry, I made a mistake, that should be 23. Okay, so what's going to happen now is you're going to partition around the 23. There's nothing to partition around that, and so you're going to partition around the 23. And basically, everything here is less than 23. So you're going to have 21, 18, 15. You're going to have 5. It's not going to touch 5. The 12, 9, 8, and 23. Okay? Okay, that's your pivot, but you leave it right where it is. So now you have stuff over here and over here. The point is that every time you partition, what you do is you're only taking off one element. Okay? And you keep on doing that. The idea is as follows: how much does quicksort work? Well, okay, it's going to have to, when you have such a well-structured thing, okay, it's going to have, it's just going to pull, you're going to do n operations to partition, okay, and then you're going to have either a left side or a right side, but a left side or a right side is going to have nothing. So we'll have plus t of 1, which is a constant, plus t of n minus 1, plus n. Okay, so basically what happens is you take off an element. Every time you're doing a partition, you're taking off one element. That's not very helpful. Okay, taking off one element is not very helpful. What would be helpful is if you chop it somewhere in the middle, because that does more. Okay, so let's do this. Okay, so this forget about that. So basically it's t of n is equal to t of n minus 1 plus n. Okay, now let's just plug in 5 here. T of 5 is equal to t of 4 plus 5. Okay, what's t of 4? This is equal to 4 plus 5. I'm sorry, damn. This is equal to t of 3 plus 4 plus 5. Okay, keep on doing this. And what you can have is this is equal to 1 plus 2 plus 3 plus 4 plus 5. Okay, and we saw this with the Gauss trick. Okay, so this is 1 plus 2 plus 3 is 6 plus 4 is 10 is 15. This is the trick, the sum of I equal 1 to n of I is equal to n times n plus 1 over 2, okay, and that's equal to n squared plus n over 2, which is O of theta of n squared. Okay? Anyways, but the point is, when you just take out one element, of your thing, of your partition, of your list, and partition, and you only take out one element, then you're just going to the next time you're going to partition over one thing. So there's no left and right anymore. What there is what was, and you take out one thing, and then you have the rest. So that's n squared. Okay, good. Let's go on. 7.3 number 2. 7.3 number 2. Okay, let's erase this. It's the same type of question. When randomized quicksort runs, how many calls are made to the random number generator in the worst case? How about the best case? Give your answer in terms of phi notation. Okay, how many calls? So here's the random number generator. You have a bunch of numbers, x1, x2, x3, x4, xn. So rather than partitioning around, pivoting around the last element, you randomly choose an element and you pivot around that. So let's go through it. What's the worst that can happen? So we'll do the worst case first. What's the worst that can happen? The worst that can happen is the number that you pick is either the highest or the lowest. Okay? And in that case, you have exactly what we did 2 minutes ago. You do n operations to partition, okay? And if you have the highest or the lowest, then what's going to be left is n minus 1 elements, okay? And you get this, and this is exactly, not exactly, but it's in n squared. Okay? That's the worst that can happen. Okay? The best that can happen. Okay, you ask for the best, doesn't ask for the average. The best that can happen is you're going to get a great partition element. Okay, and you're going to have the left case side is going to be n over 2. I'm fudging about floors and ceilings. I'm not interested in floors and ceilings. The right side is going to be n over 2, and you do the n operations. So this becomes T of n is equal to 2, it's the same thing, of T of n over 2 plus n. Okay, you can use the master theorem about this, but this is a member of n log n. What takes care of that? Okay. Okay, I'm sorry, so that was section 7.3. I didn't choose any problems from section 7.4. We are responsible for it, but we're not doing the heavy math, but it's a lot about that randomized partition. So we talked about a randomized version of quicksort, but we didn't pick any problems. So that takes care of that. I hope you enjoyed it. Quicksort is a fun and interesting thing. This partition algorithm will be used also later in Chapter 9.